ordered set. So a well ordered set is a partially ordered set in which every non-empty set has a first element. So a partially ordered set is called well ordered set. Every non-empty set. This is the first example. And obviously therefore W itself has a first element because W is a non-empty subset of the total element. A well-ordered set will have a first element and every non-empty subset will also have a first element. Now I gave you a number of examples. I don't remember. Some of the standard examples. This is not, and these are all not well-ordered sets, but they are totally ordered. But they are totally ordered. Well-ordered sets are totally ordered, but the natural numbers with the less than or equal to, that's a well-ordered set. But if on the same natural numbers I put divisibility condition, partial order, not a well-ordered set. I'll look at some more examples, but what this says is on the same set, some partial order may be a well ordering, some other partial order may not be a well ordering. Given a set, we don't even know whether there is at least one partial order which will be a well ordering. Okay, so given any non-empty set W, does there exist at least one partial order on W such that W with this partial order is a well-ordered set? So we call this partial order as a well ordering, okay, then we call it a well ordering. Now the answer to this question, that it is possible to get a partial order for any given set which makes it a well ordered set, is known as the well ordering theorem. So today's our goal is, hopefully we'll achieve this. Today's goal is to get the yes answer for this. I will put question mark. What do you mean by yes answer? Okay, anyway, that is, we will eventually prove a theorem known as the well ordering theorem. What does the well ordering theorem say? Given any non-empty set W, there exists a well ordering of W. That is, there exists a partial order such that that becomes a well ordered set. This is known as the well ordering theorem. This is the tragedy of this. We had Thorne's lemma, then we had Tukey's lemma, then we have Hausdorff's maximality principle, now we have well ordering theorem, okay, and then finally I will state axiom of choice. Two of them were lemma, one of them will be a principle, one of them we call a theorem, one of them we call an axiom. But it turns out all these are equivalent. What you call as a theorem is an axiom. If one of them has to be made an axiom, then all the others are available. If you don't make any one of them an axiom, everything is gone. Okay. So that's what we eventually see. So it's a misnomer in the sense that some things got called theorem. Call this as an axiom and get the other as a theorem. Okay. Anyway, that's our goal. So to this goal, I am going to do certain preliminaries which are very simple. I will try to explain them through some examples. Okay. So first of all, consider O, the set of all odd integers. Okay, the set of all odd natural numbers. That is 1, 3, 5, etc. All those odd numbers. I will use this notation I have probably introduced before. E, the set of all even natural numbers. 2, 4, 6, etc. And of course, n is the set of all natural numbers. Of course, n is O union. I will introduce some more of this, but right now, let us look at this. So, we already have n is a well ordered set, is a well ordered set, and is a well ordered set. Okay. Now I am going to define a different well ordered ordering on the natural numbers. Okay. So now this is a 1. We shall now define, I suppose I gave this example last time. We shall now define another partial order on n, the set of all natural numbers. And it goes like this. We define A precedes B for AB in n. Suppose I have to take any two natural numbers, then I say A precedes B if any one of these conditions happens. If 1, both are odd and A is less than or equal to B, 2, both are even and A is less than or equal to B. Now, if one of them is even and one of them is odd, these are the only possibilities. If you pick two natural numbers, the possibilities are both are even or both are odd, or one of them is odd and the other one is odd, even. I put the odd one as the smaller one. So, if A is odd and B is even. Okay. Now you can verify that since any two are comparable now. Give me any two numbers, I already have a comparison. If they are odd, I compare by the first one. If they are even, I compare by the second one. If one of them is odd and the other one is even, then the third one tells you how to compare them. So any two are comparable. It's a totally ordered set, and it is also a well-ordered set. Take any non-empty set. If it has an odd integer inside that, then the smallest odd integer is the first element. If it has only even integers, then the smallest even integer is the first element. So every non-empty set has a, so this I will use the dangerous word, clearly this is a set. So clearly this is a well-ordered set. See, on the same natural numbers, this is a well-ordering, that is also a well-ordering. What we have got is also a well-ordering. Now what happens in this well-ordering is, all the odd fellows come in their order, only after they are all exhausted, the even fellows will come, if you are really saying they are marching, okay. So basically this looks like this, 1 less than equal to 3, less than equal to 5, etc. And finally it starts with 2, 4, etc. So that's a peculiar ordering of the natural numbers. I will give you another ordering just to illustrate what we are going to do, because they will serve as examples to what I am going to do. Again, the third, another ordering, just for fun. Okay. Then you will see you can get all kinds of examples of your own. Now what I am going to do is, if both are odd, first thing is both are odd. If both are odd and A is less than or equal. So the odd ones, I know, if both are odd, I know how to compare them. Okay, the smaller one precedes the bigger one. But the problem is, if one of them is odd and the other one is even. As before, I will put all the even ones to the right of the odd ones. So A is odd and B is even. What is now the left? If both are even, okay. Now if both are even, I am going to do the following. See, for example, you take 4 and 18. Both are even, but one of them is a power of 2. The other one is not. So if I have two positive integers, one of them is a power of 2 and the other one is not, the power of 2 comes first. Okay. So let me write. If A is of the form 2 to the n and B is not, A and B are even. Okay, let me write. A, B even, A is a power of 2, B is not. See, one of them is a power of 2 and the other one is not a power of 2. What if both of them are a power of 2? The remaining thing is what? Both of them are power of 2 or both of them are not power of 2. Okay, that we will do. If A divides B, if both are power of 2. That means the smaller power comes first and then the higher power
comes. If A divides B means A is less than or equal to B because both are powers of 2. Okay. And A less than or equal to B if both are not powers of 2. See, let's say for instance, suppose if I have 8 and 15, 15 will come first and 8 will come later. That is taken care of, odd and odd. If I have 15 and 13, then 13 will come before 15. Now if I have 10 also, then the 10 will come after 8 because when I am comparing between powers of 2 and any another even, the power of 2 will come first. And if I also want to put a 4, the 4 will come before 8. And if I want something like 12, and 12 will go there because both are not powers of 2, both are even, then the smaller one comes first and the bigger one comes later. Is that order clear? So obviously this is a, well obviously, okay, this is a well ordering. It's a very peculiar order. So this is just to illustrate something. Then N, I will use the same symbol, N is a well ordered. Is a well ordered set. So what does that mean? Given any non-empty set, it must have a first element. Give me a non-empty set. First I scan for odd. If there is an odd fellow, then the smallest odd is the first element, right? And when I scan, I didn't find any odd. That non-empty set had only even. Then I see whether there is any power of 2. Then the smallest power of 2 will be the first element. Then I see that there is no power of 2. Then only even numbers, non-power of 2, the smallest one will be the first element. So every non-empty set has a first element and therefore this is a well-ordered set. Now in this set how things come? 1, 3, 5, they are all exhausted. Then comes 2, 2 squared, 2 to the n, all the powers of 2. Then what will be the first one next? 6, okay, etc. All the non-powered even non-powers of 2 even numbers in their usual order will appear. 6, 10, etc. Okay. Next one will be 10, next one will be 12 and so on and so forth. Is that clear? This is also same natural numbers. I have 3 different kinds of well ordering. One is less than or equal to, one is this order and the other one is the third order. So there are different possible well ordering of the natural numbers. Okay. So therefore, I mean, I don't know whether in the same hall, I gave one, this or on the ground floor, I don't remember. It's a few years back. I gave a talk on ranking and rating. Is anybody there present at that time? Good. You were there? No. Good. Nobody was there. So the end of the story was that ranking and rating eventually sort of subjective. Each person can do his own thing and say, I am number 1, I am number 1, you are number 1, I am number 1. It depends on what is number 1. Who is first? You define it properly, then I will become first. Okay, so therefore here is the ranking has been haphazard, the natural numbers have been ranked. Okay, so if you are rank 2 in this, here your rank will be infinity. Okay, down the list. So that's the tragic thing. You can have several orderings. The same set n, we have several orderings. Let us take the first one, which is the easiest to understand. Everybody is so familiar with it, we take it for granted. Okay, 1, 2, 3, that ordering. Now in that, suppose I have this n, I take for example a subset k 1, 2, 3, 4. Then k is a subposet, which is also a well ordered set. Okay, it's a subposet, sub well ordered set. I call this sort of subposet. There is something special about this subposet. What is special? The first element is there. The original well-ordered set will have a first element because it is a well-ordered set. The first element in this case is 1. That fellow is present in K. And whenever somebody is in K, everybody who precedes that fellow is also in K. So this K has this property. K is such that 1, the first element of W or N is in K, and K belongs to K implies A belongs to K for every A. If you take anybody else, whenever somebody is there, all his predecessors must be there. What do you call such a fellow? You have to give some name. Any name you suggest. Those are the first 5 fellows who have come into the room. One has come. If I see 4, I know 2, 3 has also come. So these are the first few fellows who have come in. Those are the initial guests. So we will call it the initial segment of the well-ordered set. So any such thing is called a initial segment. We call K, we call such a K as an initial segment of the poset. So what is the formal definition? So the formal definition there is let W be a well-ordered set, a subset K of W is called an initial segment of the well-ordered set if those two conditions are there. If Fw belongs to K. Fw is the first element of the well-ordered set W. That's the notation we will use. Okay. Fw, first element of W. And 2, whenever something belongs to K, then A belongs to K for every A in W and A less than or equal to K. A precedes K. Whoever precedes K must also be there. So in other words, somebody has jumped the queue and it's not there. Okay. 1 comes, 2 comes, then 4 comes. That means these 4 fellows somebody is missing, 2 is missing, then 3 has jumped over 2 and come. Okay. So that sort of thing should not happen. It should be very organized manner they have entered. When somebody has entered, that means all his predecessors also entered. It's not that he, like our auto rickshaw drivers or most of the time the two-wheeler people, they will find all gaps, okay, and get into the line. They don't, it's not like that. It's well ordered, okay. It is well ordered. Alright, so that's called an initial segment. Now let's look, O is not an initial segment in this. Why? Because 1, 3, 5, etc. have come, but 2 has not come, 4 has not come, right? So this is not an initial segment. 3 is there, but somebody less than 3 is not there. Okay, 2 precedes 3 is not there. So this is not an initial segment in this, this is not an initial segment in this. Now take the second example. Now the O is an initial segment for that. The odd numbers form an initial segment in that second partial order. So here in example 1, O is not initial segment. Okay. In example 2, O is an initial segment. Because if some odd number has come, all other previous fellows would have also come. Okay. All other smaller odd numbers would have also come. So the same odd numbers are now initial segments in this new order, but they were not initial segments in the old order. I remember there was a very interesting case several years ago, which was very well discussed in the newspapers. The central government has a very peculiar way of promoting people. The only thing that counts is seniority. Your efficiency has no role to play. Okay, so therefore it depends on how many hours you slept in the office, essentially. The more number of hours you have slept, then you have got a promotion. I hope no central government fellow is listening. Anyway, so there was a case of a central government department where a gentleman was in the seniority list number 3. So he was basically right at the beginning of the initial segment. Okay, but then suddenly for some reason, for whatever political, influential, etc. reason, the central government brought in a peculiar rule because of which the seniority list was revised. And this fellow 3 went to 273, its ranking. So the guy was expecting promotion day after tomorrow. Suddenly he found that he had to wait for several years now. Because unlike in the institute where after 5 years whether the vacancy is there or not, you are promoted. Okay. You are reviewed, so-called review takes place and you get promoted. But in central government you have to have a vacancy. Somebody has to retire, die or whatever it is, then vacancy must come. And so this fellow went to court. This court, the Supreme Court, etc. discussed for a long time and finally struck down the government's new partial order or well order and brought back the old order. So the order is different in the different contexts. The same fellows who were initial segments here all the odd fellows get promotion first. Then only the even fellows. Here it's not like that. So the odd fellows who are not initial segment in this order, they become initial segments in this order. What about here? The odd fellows are initial segments and the odd fellows union, the powers of 2 is also an initial segment. They all come first. Right? So whenever somebody is there, anybody predecessor is also there in that order. So that is what is meant by an initial segment. Okay. So here in example 2, shall I write somewhere? Yeah. In example 3, I will erase this trivial example now. In example 3, O is an initial segment. and O union I will call it as E2, even numbers which are powers of 2, okay, is also an initial sigma. Okay. I'm going much slower than what I anticipated. Anyway, so remember, I set a goal saying that I am going to prove the fact that any set is going to have a well ordering. That was our goal. That given any non-empty set, there exists a partial order such that makes it a well ordered set. That's our goal. So now we will move towards that goal. So I'll erase all these examples. I hope you remember these. Okay. So our aim is well ordering theorem. That is, given a non-empty set X, get a well ordering. So there exists, okay, there exists a well ordering on X. So our aim is to get this possibility that there must exist a well ordering on X. How do we go about doing this? And basically this is connected to what is known as transfinite induction, etc. But let me do it a little bit. So what I do is I have this set X. Okay, that's my set X. I want to first get an entry into it. First of all, for example, I don't know what to do with this guy. He's such a he's huge set. He's an infinite set. I don't know whether I can handle this guy at all. Okay. So what I do is make the humblest beginning. Take a piece of that. What is the smallest piece I can take? A singleton. Now take a singleton subset. Will it be a well-ordered set? Whatever order you put on that, it will be a well-ordered set. So, at least now, okay, now I can answer one question in the exam. Okay, so therefore now what I do is I get a little bit greedy. Then I take one more fellow, 2 fellows, 3 fellows. But if I continue like this, I will finish only countably infinite number at most. But the set can be uncountably infinite. So that's where mathematical induction will move from to transfinite induction. So what we are going to do is, well, okay, now I will know what to do. I will take subsets. There are subsets which can be made into well-ordered sets. So what we are going to do is let Wx be the collection of all well-ordered sets W. Now, in order to show that the well ordering may depend on the set W I have taken, well ordered sets W where the carrier set W is part of X. So I am going to look at patches inside and possible well orderings that exist for that W, right? I am looking at patches, various patches in W for which I can get well ordering. I know at least one patch, namely singleton set. So therefore that collection Wx is a non-empty collection. There are many singleton fellows sitting inside. So Wx is a non-empty collection. Collection of well ordered sets with the carrier set being a subset of W. Subset means it could also be equal to X. If it is already equal to X, if there is one well-ordered set where the whole patch is taken, I am already done. I already have a well ordering on X. So the trouble comes, I am looking only at subsets. There is, suppose I do not know that X is possible, at least I am patches I am able to do. Now what I do is, on this collection of well ordered sets, I am going to give an order. So on Wx, we define a partial order as follows. Look at it carefully. That means I want to compare two elements in Wx, but the elements in Wx are well ordered sets. So I want to compare two well ordered sets. Okay. So if W1 and W2 are in Wx, we say I will use this symbol for this partial order that I am going. W1 relation 1 is related to W2 if something happens. Give me two partial orders, I will say one of them is related to the other if the following condition satisfied. If not, I will say they are not related, because I am talking only about partial order. Okay. If certain conditions are satisfied, I will say these two fellows are related in this way. Otherwise, they are not related. What is the relationship? If I written if, okay, 1, W1 equal to W2. See, whenever I have a partial order, I must make sure that everybody is related to himself. That reflexivity must be there. So I am disposing of the case W1 is equal to W2, but then the order also should be the same, and the order is equal to this order. That takes care of the fact that everybody is related to himself. Or 2, W1 is smaller than W2. W1 is a smaller set. So let me draw a picture now. Here is X, here is W2, here is W1. Right? This fellow W1 must be an initial segment in W2. But be careful, what do I mean by W1 must be an initial segment? W1 is thought of as a subset of W2, and I have to apply the W2's partial order to W1, because W1 is also a part of W2, so that partial order will apply to it, and in that partial order, it must be an initial segment of W2. So let me write it, that is, and W1 is an initial segment in W2 and that's not enough. Now this W1 fellow is confused. At one time you are looking at me with the partial order W1 and again time you are looking at with the partial order 2. That fellow said, please remove that confusion. So what should I mean? What do I mean by that? Every pair of elements in W1 are one related if and only if they are also two related. In other words, the two relation restricted to W1 is the same as one relation. Okay. If and only if, what should I say? W2 restricted to W1 is this. W2 restricted to this is W, this relation 1, or that is AB in W1, then A is 1 related to B if and only if A is 2 related to B. In this relation also they are related, this relation also they are the same relation. W1 being part of W2, the 2 relation also applies to him. So there are two types of relation that W1 is subjected to, and that confusion must disappear. Okay. There are many ways of stating it. I am stating it in great detail so that you see exactly what happens. Okay. So what it means is, this fellow is a smaller set than that fellow. First arrange all the W1 fellows. Which order? You choose the 1 order or the 2 order, it does not matter. They will come in the same order. When you exhaust them, put the remaining fellows from W2. See, look at W2 minus W1, that's a non-empty set. And therefore, it will have a first element. And therefore, all these W1 fellows will come before the first element of W2 minus W1. And all others are W2 minus W1 fellows will come after this first element, which means all the W2 minus W1 elements come after W1 element. That is, this fellow is a initial segment. Is it clear? So, basically what it says is, I start with this and append some more elements to get a bigger partially ordered set, and that new partially ordered set, that relation when restricted to the starting part, it is the same with the old one. Okay. So therefore, we say W2 to relation is a continuation of W1. This is the continuation relation. Then we say W1, W2, this relation is a continuation of the partial ordered set W. So how we order the well ordered sets is, if I have two well ordered sets, I say this fellow is related to this fellow if he is a continuation of this fellow. That's the simplest thing. Okay. Now, if it's not a continuation, then there is no. For example, if I take the natural numbers as my set X, I take odd less than or equal to, even less than or equal to, or odd less than or equal to, and n less than or equal to, then n less than or equal to is not a continuation of odd less than or equal to, because the even numbers start coming in between. But if you look at the second relation I gave, there n is a continuation of odd. I have all the odds and then the new relation restricted to the odds was the same as the old one. A is less than or equal to B when A and B are both odd. Now we look at the third relation, odd followed by powers of 2. That is a extension of odd or continuation of odd. And then odd followed by powers of 2, followed by the remaining even numbers with that order. That is a further continuation of this. So, odd, then a bigger continuation, then a bigger continuation. Now, what do you see? We can therefore define chains. Chains of well-ordered sets. If I have a collection of well-ordered sets Wx, in that I have defined a partial order, namely continuation. Then now I can talk about a chain in this collection. If any two fellows, one of them is a continuation of the other, then it is called a chain. Okay. So then, then this becomes a partially ordered set. You can, because anybody is a continuation himself. If I have one order, well ordered set, then a continuation, then a bigger continuation, then a transitivity goes. That fellow is a continuation of this. And if this fellow is continued by this fellow and that fellow is continued by this fellow, then the only way it can take place is both are same. Okay. So these are all very easy to see. Therefore, W, the collection of all partially ordered set with this relation is a partially ordered set. Now the rest of the ball game is following. I already seen that we can see chains, then it reminds us of Zorn's lemma. We show that every chain is bounded, upper bound, therefore it has a maximal chain, which means what? A maximal element. What does that mean? There is a maximal well-ordered set, right? That will have a carrier set. Show that the carrier set is the whole set, and therefore you have got a well ordering on X. So the sequence of arguments is, then we proceed as follows. One, show that in the poset every chain has an upper bound. The upper bound, every chain C has an upper bound in the partially ordered set. And therefore, step 2, apply Zorn's lemma to conclude that this partially ordered set has a maximal what is an element? A well ordered set. So maximal element W naught namely a well ordered set W naught such that the carrier set is contained in X and W belongs to the chain implies W is contained in. This is an okay, maximal element. This is okay. I am still at upper bound such that W belongs to Wx implies and W naught implies W naught alpha naught equal to. This is the definition of maximality. Nobody can succeed him. So therefore, if somebody succeeds, he is the only fellow who can succeed. This is the definition of maximality. W naught, that W naught will be contained in X. Because the carrier sets are always parts of X. All these well-ordered sets are constructed with carrier set in X. So that is the second step. Apply Zorn's lemma to get a maximal element. Step 3, show that W naught is equal to X. So conclusion, W naught is equal to X is a well-ordered set. QED. We have made X as the well-ordered set. We have got a well-ordering on X. The original set X has been made into a well-ordered set. This is a standard trick actually in many of these cases where you want to prove something maximal. Okay. What did we do? First we take the set X. Then we looked at all possible well-ordered sets whose carrier set is in X. Then we took this box full of well-ordered sets and we imposed the partial order on them. And that partial order is a continuation partial order. And then we showed that with this partial order, any chain of these well-ordered sets must have an upper bound by Zorn's lemma. Then applied Zorn's lemma to show there must be a maximal well-ordered sets in this. Then showed that the carrier set of this maximal well-ordered set must be the original set X. And therefore, that partial order you got on that maximal set is actually a well-ordering on the original set X itself. That is the line of arguments, and that's what the well-ordering theorem is. Okay. Should I go through all those steps? I'll put, these are all very fairly straightforward. I'll just indicate. You want to get an upper bound. How do I get an upper bound? I got chains. The main thing is there are sets. What is the largest of them? Take the union. Take the union and take the same relationship union. Then you will get everything. Okay. That's all the maximum, the upper bound. And once you have got the upper bound, to show that this maximal element is actually equal to X, is that suppose it is not equal to X, then there will be an element sitting outside X, outside W naught, append it and get a bigger element in that this bigger well-ordered set, thereby contradicting that this is a maximal well-ordered set. So basically the ideas are very two-line proofs, each one of them, if you understand what exactly you are proving. Okay. So I'll put the details in the lecture notes. I'll skip them writing here. Otherwise it will take a lot of time simply writing again and again. So therefore, so far, what have we got? We had Zorn's lemma, which we did not prove, okay. But if we had this, we had two key. If we had this, we had well-ordering theorem. And from Tukey we got Hausdorff maximality principle. So quite a few things we have proved. Okay. But we'll add one more thing to it, namely from this we'll prove so-called prove axiom of choice. Okay. I will indicate, start discussing what axiom of choice is and so on and so forth. So therefore it looked like you proved the axiom. Why should you call it an axiom? You have proved the axiom. You had Zorn's lemma. You had this, you had this, you had, so you come from Zorn's lemma, you put well ordering. From well ordering, you have got axiom of choice. Why do you call it axiom anymore? A lemma, then a theorem, then a conclusion, corollary. Nice order, right? A lemma is Zorn's lemma, Theorem is well ordering theorem, corollary is axiom of choice. But unfortunately, what happens is it goes in circle. How do I prove Zandt's lemma? Then you come. And it turns out that all are equivalent. If you want one of them, you need the other fellows. If all these statements are equivalent, that is, if one is true, all are true. You need not have all of them true also. That is also a consistent system, and that's where all the problems about set theory started. So the way these things look like theorem, and this is looks like an axiom, but all are same. That is also an axiom. This is also an. If you want to call this an axiom, you could have called that also as an axiom. Okay. So now I am going to look at the axiom of choice. It will be very brief. If someone wants to read axiom of choice in great detail, some details about history and various things, a nice place. I still keep reading it, not understand much of it. I mean, still not understood much of it. It's not the mistake of the people who wrote that. It's my own this thing. There is I think whenever you have time, you log into this website, which is called Stanford Encyclopedia of Philosophy. Okay. In that, there is very many things interesting about 19th century geometry, its influence on religion, etc., etc. But there is one on axiom of choice. Whole section on axiom of choice, where what is the website? Does anybody remember? No, it's not Pilot. Plato dot Stanford dot edu and slash what? Does anybody remember? Oh yeah, I remember. I have it in my mobile. If I can locate it. Okay. Plato, it looks like capital. I am not very sure it's capital Plato or small Plato. Stanford.edu.entries / axiom - choice -choice. Okay. If you just or a much simpler one is what? Go to Google and simply type axiom of choice. This will appear. Okay, a website of Stanford University. It's a very interesting thing. You can go through many details, historical comments, etc., about it. So this whole encyclopedia is remarkable. And by the way, this was updated as late as I think August 2015. They keep updating. It's not that something has been put there and people forget it. It has been updated just about 3 months or 4 months back. So it's a very nice website where you can read the various details of this axiom of choice. That's one place. From there you will get other references. Okay. All right. So just to introduce what is axiom of choice, the terminologies, I will just begin with the following. Suppose I have two sets, A1 and A2, two non-empty sets. Let's say A1 is the set of people in Karnataka and A2 is the set of people in Tamil Nadu. Okay. Well, assume there are people in Karnataka and they are non-empty. Tacitly, when I give this example, I say they are disjoint, but not necessary. I am not assuming disjoint. Just to understand, think of that. Okay. Then what I want to do, I want to get a representative from each one of these states. That's all. I want to form a parliament consisting of one representative from each state. In other words, what I want to do is, I want to take a function from this to the union such that F1 is a representative from A1, F2 is a representative from A2. The second they be both same, yes, we will allow that also, doesn't matter. So, F1 is a representative from A1, F2 is a representative from A2. Okay. Now, this function can also be thought of, suppose this F1, if now look at F1, F2, where is it? It is in A1 cross A2. So, the function from that index set, the sets are indexed as 1, 2. There is a function from the index set to the union that can be interpreted as an element of the Cartesian product of the two sets. There is a special type of function from the index set to the union. What is the speciality? The value of that function at any one of the index is in that particular indexed set. Okay, that's what the value is. So, this is called a choice function. Such a function is called a choice. It chooses a representative from A1 and a representative from A2. And any choice function like this can be interpreted as a element of A1 cross A2. Now we extend this definition. In general, given any collection of non-empty sets, any element of the Cartesian product is actually a choice function, a function from the index set to the union so that f of alpha is A alpha. So, okay, so let us write that. So, now generalize this, let A alpha can be in any index set. That index set can be finite, countably infinite, uncountably infinite. For example, take the time interval 0 to 1. For every time, there may be a corresponding set. So, for every t, I have a AT. So, now the index set is uncountably infinite. So, we may have a countably finite number of sets, non-empty sets, or a countably infinite number of non-empty sets, or an uncountably infinite number of non-empty sets. So, where I is an index set, where I is an index set, whatever size b. B, a collection of non-empty sets. By the Cartesian product of all these sets, we mean a function f from the index set to the union such that f of alpha belongs to A alpha for every alpha. Okay. Such a function is called a choice function. The question is, given an arbitrary collection of non-empty sets, does there exist a choice function? Or in other words, given a collection of non-empty sets, is the Cartesian product non-empty? Okay. The Cartesian product is actually the collection of all, is a choice function. Is there at least one choice function? That looks like a ridiculous question, right? What is that? From each set you pick one. What do you mean by pick one? When are you going to finish it? It's not a mathematical proof. right? I picked one, I picked from J2, then I can at least use induction if the set was mathematical induction, or Peano's axiom if the set was countably infinite collection. But an uncountable infinite collection, it simply don't know, because I have finished this, I have to go to next, but they may not be well ordered. The index set may not be well ordered. After picking this, whom do I go next? So I have to invoke well ordering. I have to get some well ordering of the index set and then proceed. That's what essentially the transfinite induction is. So that is equivalent to the axiom of choice. That there exists such a function is what is the axiom of choice. So the axiom of choice is, given any collection of non-empty collection of non-empty sets, then there exists a choice function. That is an axiom. Okay. Now, if you allow me the well ordering theorem, as I just mentioned, indicated, I will use a well ordering to get the choice function, to show how the choice function can be constructed. But if you don't allow me the well ordering, then I don't know how to construct. So that becomes, therefore, these all become axioms. So what I will do in the next class is just half an hour axiom of choice, and then our discussion on set theory. For the time being, I will close. I will keep coming back to it again and again and again. Something or the other will be needed. It is difficult to anticipate everything and put. Then it will become a course on set theory. Should have analysis. I already spent how many hours now? 8 or 9. 9.5 say. So let's make, that's reasonable justice. Then beyond that, it will become injustice to analysis, the analysis part of it. So next time, half a class I will do with axiom of choice, and then get into real number system. Okay.